Welcome to the Aginex conference. I hope that there's nobody that's coughing too much. I'm here today to talk about software development in 100 years' time. That might seem like a rather unusual topic of conversation, but I've been thinking about software engineering for some time and having lots of conversations with various people on that topic. And I was engaged in such a debate with somebody in one of the social media forums recently, and they said something that resonated with me. They said if we were able to establish principles for software engineering that were really engineering principles, they would be as true today as they are in 100 years' time. And that kind of started me thinking, and that started me thinking about trying to find those foundational principles, but also thinking about, so what would software development look like in 100 years' time? And I found it a useful exercise, so that's why I'm talking to you about it today. One way in which we can start walking into this problem and start thinking about it is that if we're interested in what software development looked like in 100 years' time, what did it look like 100 years ago? And if you're like me, you're probably assuming that 100 years ago it looked rather like this, nothing at all. There was nothing going on 100 years ago. And that's kind of partially true. There certainly weren't too many mobile phones around then, but in principle that's not correct. There were some devices that were kind of at the start of what we would today think of as the software revolution. Here's one of those things. This is the Hollerith Machine. And the Hollerith Machine was designed to help automate some of the processes in the census, in the US Census in this case. Here's one of the first computer programmers programming the Hollerith Machine, and here's the program that she was using to execute what's going on. It's clearly not the same kind of technology that we're familiar with, but there are some principles here that are interesting from a software perspective. One of the things that's really so first of all, this is a binary code, which is fairly evident from the punched card that's being used. But there's also this. This is the algorithm that the Hollerith Machine embodied. And one of the things that's kind of interesting, I think, from these sorts of terms, is that if you were presented with a problem, a similar problem, this is probably the same algorithm that you would write. So there seems to me to be something fairly fundamental in the nature of algorithms. There seems to be something about a level of detail, a level of abstraction at which we need to operate in order to be able to instruct computers to carry out useful work. So moving on, the next thing that's probably important to get out of the way as we talk about some of this stuff is that there's a big assumption underpinning this talk. And that assumption is that in 100 years' time, the entities that are doing the computer programming are still us and not them. If it's them, then things might be different because they don't have the same limitations, the same capacities as we do, and so they may operate differently. But we're going to explore that in a bit more detail. But from a working assumption, they're not the ones doing all the programming. One of the fundamental principles, though, given that assumption, is that whatever software that we create, it's got to fit inside a human head. A large part of the problem here is managing the complexity of the systems that we create in order to make them conceivable, to be able to rationalise about them, to be able to think and understand what's going on. And that's a limitation, and so we need techniques that are going to allow us to constrain the system so that it fits inside human heads. So let's start thinking about some of the properties, the attributes of software that might be important in 100 years' time, the things that are going to give us a significant step up, a significant advantage. And I think one of the things that traditionally we as a community tend to think about is this: programming languages. So are programming languages going to give us the significant kinds of step changes that we might hope to achieve in order to make software development in 100 years' time, radically more effective, radically more efficient than it is today? And I would argue that no, that's not the case. I don't think that language per se is the solution to this problem. In part because of the problem that I've already alluded to. There seems to be something fairly fundamental about the nature of problems and the abilities of at least our digital computers to compute those problems that limits the level of detail, or rather specifies the level of detail at which we need to operate and to instruct them. So we need to there have been many attempts over the years to try and build things like graphical programming languages with consistently limited success, because they start out very nicely. It's very easy to build a software that allows you to draw pictures to create programs. And they demo beautifully, they look wonderful in a demonstration, but as soon as you start trying to solve more complex problems using those techniques, you very quickly run into the problems of how do you visually create things like variable assignment, for loops, if conditions, while loops, all of those sorts of fundamental components of programming language, whatever the nature of the programming language. We seem to need them. We seem to still use them, and the visual representation of those things is more clunky than the textual representation of those things, so we tend to go back to text. So there's something about this level of abstraction. Now, people like writing new programming languages. There are lots of programming languages, and that's another reason why I don't think that these are necessarily the solution that we are looking for. There are many new kinds of programming languages. New programming languages pop up all of the time. And unless you are a religious zealot in favour of one of these languages or another, I would argue that the differences between them are narrower than we think. There are differences between things like functional programming languages and object-oriented programming languages and procedural programming languages, but they're relatively narrow. Still, this level of abstraction is a problem that allows us, in order to be able to cope with the complexity of the things that we're doing, it doesn't really lift the level of abstraction significantly. So I don't think that there's anything significant going to change in terms of programming languages. I would argue that mostly language design is kind of about fashion. It's not that we are achieving significant steps forward in terms of productivity or the level of abstraction at which these languages can deliver. Rather, it's that we're getting more tactical advantages in reducing the amount of typing a bit to express particular kinds of conditions and so on. It's possible that maybe I'm underselling the value of ideas like functional program that give us a slightly different take on abstraction, but I think to some degree the verdict is out on that in terms of whether that proves the case or not. Mostly these sorts of changes, people like writing languages, and so mostly the kinds of things that encourage them to do so are kind of little itches in terms of the productivity of just typing rather than thinking, which is where the real level of abstraction plays in, and I don't see that changing significantly over time. So my prediction is that there are going to be no giant leaps as a result of programming language innovation. There might be some small advances, but they will be tactical rather than strategic. And I think that there are a couple of reasons why that's the case. The first is that there seems to be this fundamental level of granularity that applies when solving problems in digital computers. And the second is the capacity of the human head, our ability to cope with complexity. It's possible in the future that we might be able to expand the capacity of human heads by some mechanical means, but in the absence of that, that's certainly a limitation, and even if we do expand the capacity, we will still be limited by that new capacity. The next of my candidates for making significant improvements over the next 100 years are frameworks, development frameworks. And I think that this too is not really a strategic step forward. I'm currently working on an exercise in support of a new book on software engineering, which is to write a simple web application in a modern programming language and framework versus an old-fashioned 20-year-old programming language and framework. And my belief and my experience so far is that the amount of code that I write doesn't really change very much, and the level of thinking that I need to apply doesn't really change very much. So I don't think there have been significant steps forward in the past few years. They might be slightly nicer to use in some ways or not, but they're not giving us step changes in our productivity, quality or effectiveness of software development. Again, people like writing new frameworks, and there are lots of those too. Here are a few. We can look at these frameworks again, and I'm sure that their adherents will point out the advantages of one framework versus another. But again, I would argue that these are kind of tactical level advantages rather than strategic. I don't think that there's any framework that we could point to that we would argue would give us a 10x improvement in productivity, effectiveness or quality. I think that there's some stuff that we could think about that may come down the track, and there might be some signs of some of that happening. But a lot of the framework development is again about optimizing for less typing rather than less thinking, and it's thinking that's really the hard part of software development, not the typing. So my prediction for frameworks is that there may be some large steps on the horizon for frameworks. I think that some of the programming models and architectural styles, particularly around serverless programming and reactive programming, may allow us to put more of the accidental complexity of problems into the frameworks than we currently do. And if we were to achieve that, that may give us a significant step forward. But I think mostly the steps that we're likely to get are likely to be small steps rather than these significant advances through the adoption of frameworks. The next of my ideas is programming paradigm, and I would expect to be quite a lot of feedback and debate around this. Again, I don't think that programming paradigm makes a significant difference. I have lots of friends that would argue with me about this. Friends from the functional programming community or the OO community or whatever else that would argue the benefits of those different parts. I confess that I'm an old school object-oriented programmer. That's my background, that's the natural way that I think about problems, and I think that that brings some specific advantages. I think that functional programming too brings some specific advantages. So, my rather risky prediction is that in 100 years' time, programming will still be procedural, object-oriented and functional. I think those three paradigms will still be in play because they each bring different aspects of the problem. You don't learn your first programming steps doing OO programming or functional programming. Object orientation gives us the ability to deal with structure and large-scale navigation through code bases. Functional programming gives us efficiency of algorithms and the ability to use those in different contexts. All of these things bring something slightly different to the party. My controversial opinion is that I think it's fashionable these days to kind of underplay the value of object orientation, particularly in functional programming communities. And I think that object orientation did something important. I've heard people say things like object orientation failed, and I kind of laugh behind my hand if I'm honest when people say that kind of thing. If you look at the change in the scale and complexity of the software that we built before and post the introduction of object orientation, they are worlds apart. And that's not just to do with hardware capacity, but also to do with the ability to abstract problems more effectively in an object-oriented programming paradigm. It also gives us the ability to navigate code bases more effectively. And that's something that I think that the jury is still out in functional programming problems. My perception and some of the feedback that I've heard from functional communities is that that can be a problem in large-scale developments, because the navigability of the software is more difficult because the concepts that you're dealing with are abstract and spread throughout the solution. So I think object orientation will still be in place. I think it has made a significant contribution, and I think that the others will be in place too. I think one area where there is room for innovation is in the area of services. I think that the idea of service-based computing is kind of an object-oriented idea, but the idea of composing systems into small bubbles of behaviour that are encapsulated and isolated from others is an important one. And None of the languages, none of the mainstream languages certainly provide that as a sensible level of abstraction. And I think it would be a good thing if they did. If we could code for a service boundary rather than using programming conventions to kind of hint at a service boundary, I think that might be a step forward. So my, again, slightly risky prediction is that I think that there will be some advance in our ability to encode for those sorts of larger structures in software systems. The next on my list of candidates for things that will be durable and that can have a big impact is test-driven development. Those people that have seen me talk about software development before will know that I'm a big fan of test-driven development, and it probably won't surprise you to think that I think this is a candidate. It's not, I've coded this as amber rather than red. I haven't completely ruled this out as an advance, but I think that there are some concerns about it. So why not? Why hasn't test-driven development already taken over the world, and why won't it? And in part, that's because we got the words wrong. When test-driven development was created, we talked about it, the phrase test-driven development immediately starts you thinking about testing, and the vast majority of people that are exposed to it understand test-driven development as a testing approach. And it's not, it's a design approach. So my prediction for test-driven development is that it will become a cornerstone of software development and software engineering. It just won't be called test-driven development. We'll call it something else. But the practice of expressing the executable specification for our code before we create that code that is inherent in test-driven development will become a norm for professional software development. My ambition is that when my granddaughter learns to program her first line of code in kindergarten, she learns that in the context of test-driven development, or whatever we call it by then. Some ideas are more durable than other ideas. So what are the ideas that we think might be valid in 100 years' time? I would argue that software engineering is principally about two things. Managing complexity, being able to keep the work at a scale that we can fit inside a human head, and optimizing for learning. We want to be able to learn, explore, interrogate the problem space, the technology, our procedures, our techniques, our teamwork, all of those things in order to be able to develop those and improve them continually as part of the evolution of our software. And I don't think that's going to change. That works better than anything else. Software development is always an exercise in exploration. I think one of the tragic mistakes of our industry is to misapply production line style thinking to solving problems in software. Software is never a production problem. Production for us is easy. It's just a matter of cloning the bytes that we've created. Our problem is always a design problem, and that's about exploration and learning. So what are those ideas that in that context? My first set of ideas are really about optimizing for learning. And those are ideas of iteration, feedback, incremental development or incremental design, working experimentally and working empirically. These ideas, I think, are foundational to our ability to explore ideas and create new things. These are the ideas, I think, that are genuinely candidates for being durable, for being true in 100 years' time. I think I can't imagine any endeavour that human beings undertake that involves learning that doesn't require these things at their heart. Our ability to get feedback back to the point at which we're creating ideas, work iteratively to manage that feedback, work incrementally so we can modularize our system and think about pieces of it at a time, work experimentally so we can try out ideas and see what works and see what doesn't, and work empirically, discover from production what's really happening and which of our theories are mistaken. These are foundational concepts. They're grounded in our need to learn and deepen our understanding. Software development is and always will be an exercise in learning and discovery. We need to organise for that. We need to become experts at learning and discovery. My prediction in this context is that even if the machines are the ones that are writing the code in 100 years' time, they'll still be using these techniques because these aren't really specific to human beings. These are appropriate to any kind of intelligence that is involved in learning and discovery. This is how you learn and discover new things, even if you are a machine. So my prediction here is that software development in 100 years' time will be based on these ideas. It will be founded on these principles, and however sophisticated everything else is about the software development process, these will be the foundational ideas that underpin that exercise in learning, discovery and creativity that is software development. There are huge steps, huge progresses to be made by adopting these techniques and applying them into our development process. We are already seeing the beginnings of that with ideas like continuous delivery, but there's more to do in being more experimental, more learning focused. I'd like to make an observation. In 1986, Fred Brooks, the author of The Mythical Man Month, wrote a seminal paper in which he said there are no silver bullets. There are no improvements in technology or practice that will give you a 10 times improvement in software development, productivity, quality or efficiency. And I think that at some level Fred was correct. I think that's true. But I also think that there's a counter to that Fred didn't talk about in his paper, which is that there are such things as mud bullets. There are things that don't work, things that are wrong, and our industry is infested with those. If you are working in an organisation that's practicing waterfall methodology, you're not using source control, you're not doing automated testing, then you are not taking advantage of what really works, and therefore there are definitely orders of magnitude of improvement in quality, productivity and effectiveness in those kinds of environments. One of the things that we haven't been very good at in our industry is eliminating the bad ideas. So it's not just about adopting or coming up with new good ideas. I think we know what works to a large degree in software engineering these days. The problem is that we don't apply that kind of thinking and we don't adopt those sorts of practices. So it would be good, it would be a huge step forward if we were able to discover a way in which we could eliminate the bad ideas and stop working on effective, archaic, inefficient practices. The next set of durable ideas are slightly more technical. These are about fitting stuff inside a human being's head. And I think in this category there are ideas like modularity, separation of concerns, information hiding, abstraction, and cohesion. Again, these are more technical terms. These are terms that we've kind of been familiar with for a very long time in computer science and in software development circles. But we don't necessarily widely practice these things in day-to-day software development, and we should. These are effective strategies that allow us to develop higher quality software more quickly, componentize it in a way that we can work in one place without having adverse effects in another, and move forward more quickly by separating development out into large teams, the kind of microservices, Amazon small team style of development. These ideas are foundational to software development at every scale. This is just as true if you're writing some assembler to run on a chip as it is if you're writing a global distributed cloud-based system. These ideas are foundational, and we should be applying these and adopting these sorts of techniques in the design of our systems all of the time. We need to decompose ideas into pieces that are small enough to fit into a human being's head. Software development is about learning and managing complexity, and so we should be optimizing to be really great at learning and managing complexity. So my prediction, even if we do enhance our cognitive abilities through electronics in 100 years' time, I would still predict that software development will be driven by the need to fit inside even our newly expanded human heads. So even if we are smarter than we are today, there will still be a limit, and we will still need to work within those limits in order to be able to build sophisticated software systems. So my observation is that software development is about learning and discovery. Humanity's best technique for learning and discovery is the scientific method. If we start applying that kind of thinking to solving problems in software, we get dramatic, measurable, demonstrable improvements in productivity, quality and effectiveness of our solutions. The ideas of incrementalism, iteration, empiricism, experimental practice and feedback are foundational to our ability to practice in this more scientifically rational approach. These are the tools of the trade of science and Enlightenment style thinking that we can think of as genuine engineering in our context. As I've said, software development is also about managing complexity. And so that is about our ability to compartmentalise things, modularise things, work with separations of concerns and so on. These techniques are focused on our ability to fit problems inside of human beings' heads. If you didn't think that I was arrogant enough to put continuous delivery up as one of my candidates, you don't know me very well. Continuous delivery, how does that stand? I think that continuous delivery does have an opportunity of being valid and correct in 100 years' time, because it's based on these principles, it's based on these foundational techniques. CD is based on the application of the scientific method to software development. That's why it works, that's the reason why it's so effective. The scientific method is humanity's best problem-solving approach. That isn't going to go out of fashion, that's not going to change, that's not going to be different in 100 years' time. And so applying the scientific method and that style of thinking to solving problems in software is our best hope of success. Continuous delivery has at its heart the ideas of iteration, feedback, incremental development, incremental design, experimentation and empiricism. It's built on those feedback-driven approaches and our ability to learn and adapt as a result of what we discover through its mechanisms. So continuous delivery through automated testing encourages modularity, information hiding, separation of concerns, abstraction and cohesion. The combination of this platter of techniques allows us to optimize our development process to focus both on the management of complexity and on optimizing our ability to learn and to discover. So continuous delivery is profoundly an exploratory approach to software development, and I believe is an example of applying that kind of scientific style reasoning to solving problems in software. So my prediction is in 100 years' time, even if the machines are writing the code, they will also be practicing continuous delivery. Thank you very much for your time. I hope you have a great day, and I hope the rest of the conference goes well. Thank you.